Yeah, it's starting now.
Okay. All right. Thanks for joining us as EPSP Connects, a monthly webinar series, kicks off the start of another year. I'll just remind everyone that our purpose here is to bring those working in the community together to learn about new research and initiatives going on. And it's all volunteer. And so the only way it can keep going is through volunteered effort, which is significant, both on the part of invited guests who prepare and generously give their time, and also the team members who plan and host behind the scenes. And of course, all of you, an engaged audience. Joining me today is our Jimmy Geilinger and Mikey Robinson, and they'll be helping field questions at the end. Okay, and we have several new members as well that you'll be meeting throughout the term as they host. So without further ado, I'd like to introduce our speaker today, Dr. Sarah Schanz. She's an assistant professor at Colorado College, Department of Geology. She received a Bachelor of Science from Western Washington University and a PhD from University of Washington. And she did a postdoc working with Brian Ioannidis at Indiana University in Bloomington. And the title of her talk is Rocks in the River, Creating Terraces and Gorges with Sediment. So Sarah, you can take it away.
Great, thank you. I have to say, I like Risa's title that she used when advertising on Twitter better, Rocks and Rivers and Landforms. That's a much better title because we're just going to be talking about 3 case studies of sediment in rivers and the sorts of landforms they create. So more inclusive than just terraces and gorges. All right, so before I get started, just want to apologize if anything does come up, Risa, or anybody on the committee, feel free to interject. I'm down to one screen, and so I can't really see chat or video well while I'm sharing. All right, so when I was thinking about what to talk about for this, it kind of came to mind, it's the new year plus or minus 19 days, and a great time to reflect and celebrate everything that's happened in the last year. And in particular with this talk, I want to celebrate the work of 2 of the undergraduates who worked with me over the last year, Peyton Coley and Sam Bauer, who both started their theses in March of 2020, unfortunate timing for them, and then graduated last spring and did a wonderful job working through a pandemic, getting some research out. So this talk is going to be split into 3 parts, and parts 2 and 3 is really going to highlight their theses and hopefully kind of celebrate that science. I was also just kind of looking through my past photos and kind of thinking of internally my own path. And this photo on the screen here, this is from a backpacking trip I took when I was, I think, 19, hadn't taken a geology class yet, but was signed up for one. And I was just fascinated with this avalanche track here. I have so many photos of it with my point and shoot camera, just zooming in as close as I could possibly get on all of the downed logs in the channel here. And then all of this rock coming off of the hill slope, making its way through this avalanche and debris flow track into the streams. And so today's talk is going to be the decades later revisiting of this idea of what the trees in the channel here are doing in terms of sediment retention. And then we'll kind of move up valley to the hill slopes to talk about some landslide work that Peyton and Sam were doing. All right, so just a quick overview. We're going to do 3 case studies. The first one is going to be on sediment retention in mountainous rivers. So thinking about how sediment is actually moving through a river. And then we'll work our way up to how sediment is being delivered to rivers via earthflows in Washington State and deep-seated rotational slides in Colorado. And on both of these, we're going to think about implications of how sediment is being delivered, and then what's that doing to the landforms within or nearby the river channel. So the first chapter here, sediment retention, is really coming back to those kind of completely amateur observations I was making with my point and shoot camera, that when we have log jams and obstructions in the channel, they tend to trap sediment upstream and impact channel form. And probably many of us have seen this as we've been hiking or even driving, where you've got logs or other obstructions, and immediately upstream of those is a sediment accumulation. So on the left here, we've got a bedrock river that is bedrock downstream of the obstruction, and upstream of the obstruction has a armoring layer of large cobbles on top of it. And similarly on the right here, we've got over a half-meter accumulation of gravels upstream of the log jam. So what we wanted to know is, can these log jams and obstructions actually have a significant impact on channel evolution, or are they more of these ephemeral temporary features? And the Pacific Northwest has this wonderful ready-made experiment set up for us, where we have an example where there were log jams in the channel, and about 150 years ago, all of those log jams were removed via splash damming practices. So this was a popular practice in the late 1800s along the West Coast, as well as in the Rocky Mountains and probably other places that I don't know about. Essentially, over the winter, timber would be cut, piled into rivers. The rivers would be dammed, and during spring snow melts, the dams were dynamited, and large floods would rapidly kind of pulse downstream, carrying all of that cut timber and transporting it down to the lumber mills further downstream. This obviously was kind of destructive flooding, but as a precursor to this, we needed to simplify all of the channels so that the timber didn't get caught anywhere. And this basically meant removal of any pre-existing log jams and a lot of simplification and straightening of some channels. So in the middle, you can see what one of these splash dam floods looks like. And on the right, this is the impact it had on the Middle Fork Teanaway River, which is in central Washington state. It basically went from a channel that has extensive log jams on top of it to one that has almost no log jams along its entire reach and is now a mixed bedrock alluvial system. So we wanted to know, we'll go to the Teanaway River where we've noted this change. Since there was splash damming common here from 1892 to 1916, can we use this as our case study to test whether or not splash damming had a significant impact on river morphodynamics and on incision rates? And particularly we chose this because an earlier study, Collins et al. 2016, had few preliminary dates on this lowest terrace in yellow here that showed that it formed at about 1900, so about the same time as splash damming. However, we only had a few preliminary dates, and we weren't quite able to rule out any other factors that could have caused incision. And just to give you a nice visual of what this looks like, this is one of more striking landforms that was created at about 1900. This is a bedrock strath terrace. We've got a buried log jam sitting on top of that bedrock, and about 2 meters from this bedrock strath here to bedrock in the channel bottom. All right, so our hypothesis was that in-stream wood loss and loss of sediment retention had caused river incision. But we wouldn't be doing good science if we didn't think about what else could have been going on, especially at around 1900, when we have the end of the Little Ice Age. So perhaps some climate changes could have influenced the sediment supply or sediment transport in this area and caused these landforms. We could have also had some autogenic processes going on. So perhaps just constant meandering caused apparent terrace abandonment at about 1900. So we're going to go through these 3 hypotheses. We'll start first with autogenic. So play this nice video from Lay and Lamb 2016. This basically shows a simulation of a meandering river. We're looking top down and then to the side. And this meandering river undergoes a constant incision rate as it's meandering. And so you can see it creating this nice wide valley here. And as it creates that valley and incisors at the same time, it's going to leave behind landforms that are color-coded here, which are terraces. And these are terraces that are forming not through an on-off switch of river incision, but just through this constant lateral migration combined with vertical incision. So basically, there doesn't need to be this external switch to cause terrace formation. What we note here is these terraces that are formed in these simulations and in other areas where we've seen autogenic terraces, they tend to be bound by sinuous edges because they're forming through a meandering river. They're associated with a meandering river, and they tend to be sloped towards the channel, which you can see on this long green terrace here. As the river has migrated out, it's also cut down. So the terrace slope, you can see on the bottom, is not perfectly flat, but will slope in towards the river. So we use those metrics to look back at our mapping area. And so we mapped all of the terraces in the West Fork and the Middle Fork of the Teanaway River. This yellow one is the one of interest. And when we looked at the geometry of this, it really didn't follow any of those signals of autogenic formation. In other words, we don't really see any meandering signals in it. It doesn't have very sinuous edges, and it doesn't have those slip-off surfaces that are sloped towards the river channel. So that seemed to rule out autogenic formation. We also wanted to date the terraces more. So earlier we'd had just a couple preliminary dates on the terraces. And by dating them in more depth, one, that can show us whether or not these terraces formed all at once, which would be another reason to rule out autogenic formation, but could also help us differentiate between a climate hypothesis and the sediment retention or in-stream wood loss hypothesis. These terraces are a little tricky to date. They are preliminary ages put them at about 1900 AD, and that's a tricky time. Radiocarbon doesn't work well. Lead-210 would be great, but unfortunately our preliminary forays into lead-210 showed there's not enough clay in this area, and we weren't getting a strong enough signal. So instead, we're going to pair two geochronometers. We're going to use the traditional radiocarbon. So from the base of the alluvium overlying the strath, we'll collect charcoal, twigs, other organic material, and date that. That gives us a maximum age for terrace abandonment. In other words, this pine cone, for example, was deposited and sat there for a while before the river actually started to incise and abandon this terrace. We then pair that with age of trees overlying these terraces. So we cored the trees, counted tree rings, and we know that these trees couldn't stabilize until this surface was no longer part of the active river channel. And we actually sought out trees that preferred slightly drier soil conditions and likely didn't start to grow until some river incision had occurred and the water level had dropped below, significantly below the root level. So these two age bounds give us when river incision actually occurred. So we went through and did this for several sites along the Middle Fork and West Fork, grabbing tree ring data and radiocarbon ages. And you can see our swath of ages here. Radiocarbon has several frequency peaks. So we're looking at the probability distribution function for those calibrated ages. This is kind of messy, again, because this is so recent. Calibration is not a smooth one-to-one between radiocarbon age and calendar age. And then in triangles are our tree ring ages. One thing to note, the Middle Fork has about 1 meter of incision. So our y-axis here is showing us how much bedrock incision occurred. And our West Fork channels tend to show about 0.5 meter to 1 meter of incision, but in some cases up to 2 meters of bedrock erosion. When we constrain these to the ages, we get a couple different scenarios shown in blue here. One that is more kind of taking the earlier probability peak for the radiocarbon ages, which would be between about 1650 to 1950, and then one that's a bit of a narrower bound between 1850 to 1950. To differentiate between these two, we kind of looked back at the longer record of river incision in this area that Collins et al. Had compiled. And in their data set, we have a really nice set of radiocarbon ages that follows a terrace along T2. So this is the next older terrace, and shows us exactly how long it took for that terrace to be planed. And that's shown in this orange bar here. And that took about 800 years. So we know that in this area, typical planation tends to last about 800 years before we get a period of incision. And based on the fact that T1, our terrace that we're trying to date, and T2, this older terrace, have similar widths, we think we also need about 800 years for T1 to have been planed to form that broad surface. And if we look back at these two blue bounds here, the light blue bound doesn't really give enough time. It only gives 100 years for that terrace top to be formed, which isn't going to form that extensive terrace that we do see. So we think it's more likely that this dark blue bound is the bound of incision for this area. And that actually matches really nicely with both the timing of splash dam logging and the end of the Little Ice Age here. So when we do a little bit more detailed dating, again, we can't really differentiate between in-stream wood loss and climate yet. Right now, both of those align well with our dating, but we can run through a little bit of a thought experiment to see which is more likely. So for example, when we look at climate, we kind of have two factors. We've got the end of the Little Ice Age, and we have periodic fire disturbance in this area. The Little Ice Age locally in the Channaway ended about 1890 to 1900, and we know that it was about 1 degree cooler in this area overall. Although there wasn't really a change in the degree of glaciation, this area remains unglaciated. However, a slightly cooler climate could result in more frost cracking, which would result in more sediment and perhaps terrace planation, which would align up with our dates. When we look at the amount of cooling in the Little Ice Age, though, we compare this to this nice graph that Marshall et al. Came up with, where we can look at mean annual temperature and the temperature amplitude. And the Little Ice Age in the Channaway falls along this orange star here, which indicates no frost cracking intensity, or very, very low frost cracking intensity. And in fact, compared to present day, there's no change in the frost cracking intensity. So we think it's unlikely then that the Little Ice Age temperatures led to any changes in sediment supply that would have affected river incision rates. Similarly, wildfires, when we go through a thought experiment, don't seem likely as a cause. Wildfires in the Channaway tend to occur every 300 to 350 years and result in punctuated sediment delivery. So these would be short periods of high sediment loads and strath planation with longer periods of lower sediment loads in between them, which is opposite what our data sets show. Our data sets show that we have long periods of high sediment loads and planation and short periods of incision. So based on this, it seems like climate, at least Little Ice Age climate changes, are unlikely to have caused river incision, leaving behind our main hypothesis of sediment retention and in-stream wood loss causing river incision and the formation of this new terrace. One last part of this chapter, we were curious. There's a really rapid response observed, basically almost a couple years between the onset of splash damming and incision. We just wanted to check to see if that's reasonable. So we just did some quick sediment transport calculations. We estimated what the pre-incision channel would have looked like. So based on the thickness of gravel deposits on top of this terrace and the size of those deposits, we kind of ran it through a quick sediment transport calculation here using modified Meyer-Petter-Mueller equation, where essentially that flux of sediment is going to be proportional to channel width as well as the slope and height of water. So these are all factors that we could kind of extract from the LiDAR, and then we have a suite of studies that give us an estimate for what grain size should be. So we basically just modeled the Middle Fork and West Fork Channaway, just looking at sediment transport and the height of sediment over time. So model year 0 here is essentially going to be the onset of splash damming. And then we'll look at how the sediment height changes over the next 100 years. And essentially, we did a couple different runs where we varied the depth of the original sediment cover and the size of the original sediment cover. And for all of these, within the first 5 to 10 years, that sediment cover is lost, and we go down to either bare bedrock or a very thin, easily mobile sediment cover. So this indicates that the rapid timing that we see and the rapid response that we see is fairly reasonable for this area at least. So just to sum up this section, we looked at the Middle and West Fork Teanaway rivers to see if the loss of sediment retention could have a significant impact on the channel. And we did see in many places up to 2 meters of bedrock incision due to this loss of retention, which means it does have a pretty significant impact on channel dynamics. We in depth looking at the timing, the mechanism tends to match splash damming, this loss of retention, which indicates that not only is sediment retention impactful, but the human alterations that caused the change in sediment retention resulted in the formation of a new valley bottom surface, and showed that retention as well as humans can have a pretty significant impact on bedrock rivers. But this study is sort of put at the beginning as a segue into some of the work that my students have been working on, because one of the things we noted at the end of this study was that the bedrock in this area that we're looking at is the Roslyn Formation. It's a very unique bedrock. It looks kind of like this picture close up. So the eraser tip of this pencil is on a slight ledge, and then the slope of that ledge is all just falling apart into sand grains. In other words, this bedrock is extremely prone to wetting and drying, and basically doesn't form any bed load. It immediately erodes away into sand. And so there's this question of, if sediment retention in this river incision is caused by a loss of bed load, or a loss of bed load kind of retained in the channel, where did that bed load come from if the channel itself is not really producing any? And so this area in green and light green here is all the Roslyn Formation. That's all where we had just been looking. And some of these blank polygons here, actually quite a bit of those blank polygons are actually mapped landslides. And so we kind of turned this question around. We wanted to understand what's the role of landslides then in sediment delivery and channel modification, and how might this tie to the story of sediment retention that we just looked at. So in 2016, the LiDAR for the Teanaway became available, and we started just perusing it. And everywhere you look, when you zoom in, you see evidence that these hill slopes are just kind of dripping apart. There are earth flows everywhere that are bringing sediment from the tops of the ridges down into the valley bottoms. They're filling up the sort of tributary headwaters, and they're also in many cases crossing and closing some of these valley bottoms. So what's the sediment delivery from these earth flows, and when did these earth flows form? We currently don't really know much about them at all. So this was the topic of Peyton Coley's senior thesis. She started work on this in February of 2020. We had all these grand plans. In March, all of that obviously fell apart, as did, I think, many of our research plans. But Peyton was able to still complete a lot of this work using GIS remotely from home. So in studying these earth flows, we kind of focused on 3 questions. What controls earth flow location, which it tells us what stream sections are likely to receive more sediment. We wanted to know how active the earth flows are. So is there a way that we can absolutely or relatively date these earth flows and their activity? And then how do the earth flows interact with the valley bottoms? So Peyton spent the whole first few months of the pandemic tied to her laptop screen and mapping earth flows and other landslides in the Teanaway area. She ended up mapping almost, I think, over 300 landslides total. We have 187 earth flows, which are all shown in red on this map here, and then some translational and rotational slides that are in gray colors. You'll note an absence of landslides in this upper part of the basin, and that's not because we didn't look, it's because we didn't find any. So there does seem to be this lithologic control on landslides where kind of this upper basin area, which is in the Swak Formation, has no landslides or earth flows. And all the landslides are concentrated in two lithologic units, the Teanaway Basalt and the Roslyn Formation, which is a sandstone. We also looked at the aspect of all of these earth flows, and we plot out the aspect of just the earth flows. Most of them are facing to the southwest, with some facing to the southeast. And again, this follows nicely lithologic patterns. So here we're looking at a geologic map of the area. All of the landslides that we had mapped are mostly in these yellow and red colors here. So the yellow is the Roslyn Formation and the red is the Teanaway Basalt. And it's probably very hard to see, but all of the strike and dip symbols on this geologic map in the center part of this map are towards, the dips are towards the southwest. As the basin kind of curves around to the upper left or the northwest portion of this map, the dip direction changes to be towards the southeast. And those correspond with the two most common aspects of our earth flows. All right, so the bulk of Peyton's project was trying to relatively date landslides. We'd been inspired by the relative dating or the absolute dating that Lahusen et al. Had done, where they use a standard deviation of slope on rotational slides near the Oso, Washington area to date a whole suite of landslides here. Basically, as these landslides age, diffusion occurs and the surface roughness becomes lower. And that surface roughness is measured by the standard deviation of slope over a moving window. And it forms this nice exponential curve that relates roughness to the age of the landslide. So we were really hoping we could do the same things with these earth flows, but we quickly realized that earth flows are a little bit of a different beast. For one, they can be periodically active rather than just having kind of one major failure. And so that kind of complicated matters a little bit. We also noted that these earth flows don't start out with random roughness elements. Instead, they tend to have these really nice flow lineation features to them. And so we decided it might make more sense if we can take advantage of these flow features and try and find a surface roughness metric that relies on the flow direction and directional roughness. So Peyton found a roughness metric called MAD, which is a roughness metric that can be combined with the topographical flow direction to get the surface roughness in the direction of flow. We then took the standard deviation of that. So as earth flows are kind of early in their activity or as they're more active, we're going to have a lot of these flow parallel features. They're going to have a low flow directional roughness. However, because we're using LiDAR, we're able to capture the roughness elements orthogonal to that, and those have a very different roughness value, and that results in overall a larger standard deviation of roughness for young earth flows. Which you can kind of see in this inset map here. Basically, we took this Jungle Creek landslide that's shown in the DEM on the right, and we ran hill slope diffusion over that and calculated the MAD STD every 2,000 years. And it starts out with a MAD STD of about 0.146 or precisely 0.146, and then linearly decays with time over the next 10,000 years. And the rate of the decay is highly dependent on the soil diffusion. So this seemed like a promising method to try and relatively date earth flows. We then wanted to see if we could add in some absolute age controls to this. So on this graph, we're just going to be summarizing all of our absolute age controls. And for each earth flow that has a date on it, we're going to, the y-axis location is where the MAD STD value is. And so again, according to our modeling here, the MAD STD should get lower with time since last earth flow activity. All right, so shown in blue here are radiocarbon ages that we got from earth flow tows. We're showing the probability distribution function. And these gray bars here show breaks in the X scale. So we have dates that are up to 40,000 years old, one that's about 4,200 years old, and then most dates are in the last 1,000 years. However, we know that radiocarbon ages represent maximum earth flow age or maximum landslide age, and in fact can be up to 6,000 years or even more than 6,000 years too old due to carbon residence time. So we paired this with sedimentation ages from lakes. Basically, we have 3 locations where earth flows block the valley and form a lake upstream. We use the volume of sediment in that lake plus estimates of denudation rates to figure out how long those lakes have been filling up. And that gives us these orange bars here. You'll note that it's a little unusual. Our unnamed lake down here that has the youngest age has the lowest MAD-SCD, which should correlate to the oldest age. So that doesn't actually match our predictions at all. However, if we look at this unnamed lake, we see one of the drawbacks of this method, which is that earth flow complexes are complicated. So this is an inset into this area. Here's our unnamed lake. It's dammed down here, so flow is from top to bottom in this image. And then everything in color is an earth flow complex. And the colors represent the MAD-SCD calculated with a 5-meter moving window. So blue is low MAD-SCD values, and you can see that most of the earth flow complex has a fairly low value. But right next to the lake and in the area that's actually damming the lake, we see portions of the earth flow complex that have higher MAD-SCD values shown in yellow. And in fact, when we took a second look at this, there is a headscarp that's visible here, and then an offset logging road that indicates there might be some reactivation of this portion of earth flow complex. So if we just consider that this is actually what's blocking the lake, then we get a higher MAD-SCD value for the portion of the earth flow complex that's blocking the lake. That actually brings it up to be fairly similar to the values that we found for Rye Creek and Indian Creek. So very roughly, what we're getting out of these absolute age controls is kind of the messiness inherent to this method that we're proposing. So that MAD-SCD values aren't extraordinarily precise. So for example, we have 3 lakes here that are all formed at approximately the same time in the last few hundred years. But they have MAD-SCD values that range from 0.136 to 0.146. So there's MAD-SCD values of 0.01 to 0.02 range can represent the same level of earth flow activity. And that's not too discouraging. Other studies that have compared surface roughness dating methods have found that a lot of these methods don't really work in differentiating ages that are only a few hundred years apart. So that's kind of consistent with other surface roughness metrics. What we are going to try and take away from this graph, though, is that when we see MAD-SCD values that are in the range of 0.13 to 0.15 or greater, that's usually going to be correlated with earth flows that have been active in the last few hundred years. So very roughly then, if we look at all of the earth flows in our study area, we're going to divide them out by lithology, since lithology is going to be a major control on the hill slope diffusion, since the climate is similar throughout the study area. So here we're just showing histograms of MAD-SCD of earth flows within the 4 major lithologic units. The upper panel and the lower panel, which are the Slock Formation and the Middle Roslyn Formation, don't really have a lot of earth flows in them. We're going to try and refrain from drawing any conclusions from those. But when we look at the Teanaway Formation, which has 96 earth flows in it, we see that most earth flows have MAD-SCD values of 0.1, which if you remember, 0.13 to 0.15 is our earthflows that were active in the last few hundred years. So this indicates that mostly in the Teanaway Formation, we have a set of earthflows that were active earlier than a few hundred years ago, although 25% of them were active in the last few hundred years. Similarly, in the Lower Roslin Formation, we have a peak of earthflow MAD STD values that's older, and then another peak that's younger, that's about 25% of the earthflows in this formation. And again, that indicates about 25% of these earthflows conservatively were active in the last few hundred years. All right, so originally this talk kind of started with understanding what's going on in the river channel. And so kind of our last part of this study was to kind of tie this together with the impacts directly to the river channel and to valley bottoms. And so for all of the tributaries in our study area, we looked at the valley width and compared it to drainage area. Ideally, as drainage area increases, valley width should also increase, kind of like the trend seen here on Jack Creek. However, all of our dots that are colored here that aren't gray represent valley width measurements that have an earth flow impinging on one side of the valley or on two sides of the valley. And they're colored by their MAD STD, where the darker red colors are higher MAD STD and the light tan colors are low MAD STD. And almost all of our tributaries, and indeed all of them, because Jack Creek has one earth flow in it, all of our tributaries have been affected by earth flows, and these earth flows have been narrowing valley widths. So if you follow the trend of valley width versus drainage area, we'll often see that trend interrupted by some of these colored dots that indicates there's a recently active earth flow that's been narrowing the valley width. Another interesting trend here is that almost all of these tributaries start in earth flows. So there's an earth flow directly at the beginning of every tributary, which means that there's quite a lot of sediment being contributed to the tributaries from these earth flows, likely. So just to summarize what we've got so far, we looked at what controls earth flow location, which stream sections are more likely to receive sediment. We see these earth flows are lithologically controlled. So we're going to tend to see more earth flows in the Teanaway Formation and the Lower Roslin Formation, likely following paleosols or bedding plains in those two lithologies. In terms of the activity of the earth flow and the timing of sediment supply of the channel, this is kind of fairly rough data, but we think conservatively there's about 25% of the earth flows in this area were active in the last few hundred years and may still be experiencing some activity. So there's been a fairly recent pulse of sediment supply to these channels. And then in terms of how earth flows are interacting with valley bottoms, almost all of the tributaries, especially in the North Fork of the Teanaway River, are starting in earth flows. So immediately there is this influence of earth flows and earth flow sediment supply on the tributaries. And then further downstream along these tributaries, earth flows come in and narrow the valley width and actively bring in fine sediment to those tributary channels. So these earth flows are definitely having an effect on sediment transport. And then they're also changing the connectivity in some of these tributaries where they're narrowing valley width and really pinching out those valleys. All right, so at the same time that Payne was working on this, we were seeing earth flows that were blocking valleys with sediment, but channels were still able to erode through them. So in this lower left image, this is an earth flow in the Teanaway. Flow is from right to left. And you can see that this stream channel has been able to erode through the toe of the earth flow and continue on its merry way. However, what happens when this landslide sediment gets too large or has a low erosivity and can no longer be eroded? This is the case on the West Elk landslide in Colorado, where the West Elk Creek, which is flowing from top to bottom, is suddenly diverted around this landslide, and the valley sides have also kind of reformed around that landslide as well. And so at the same time that Payton was working on the Teanaway, we had Sandbauer working on this epigenetic gorge in Colorado. So an epigenetic gorge is when we have, for example, a landslide blocking the river channel, and then instead of the river eroding through the landslide material and reforming the channel in its former position, it forms a new channel position. And that appears to be what's happened in the West Elk, where we see this obvious diversion of the stream channel around the landslide, as well as a mirroring diversion of the valley wall that mirrors the shape of the landslide toe. So we're working in kind of near Gunnison, Colorado, in the West Elk mountain range. This area is made up of Oligocene andesite flows and breccias that came out of the West Elk Volcanic Center. So these are layered andesite flows and then breccias on top of that, with a fairly low uplift rates of 0.1 millimeters per year. We can see from the LiDAR that there's about 65 to 100 meters of erosion that's occurred between the landslide toe and where the channel currently is. So there's quite a lot of active erosion processes and channel adjustment going on here. But what kind of struck us here once we started doing some background research was noting that a lot of the previous research in epigenetic gorges tends to be in areas with really high uplift rates, like the Himalayas or New Zealand or Taiwan, and are mostly in crystalline rock. And here, we definitely do not have crystalline rock. We have tiny blocks of andesite in a very erodible breccia. And this view of the river here kind of shows that this is kind of, while we're facing in the direction of this white arrow on the slope map, this is a block of bedrock that's been eroded out of the landslide toe. And it's a breccia where most of the breccia clasts are andesite. And we're looking south and you can see the wall, the valley wall, intact bedrock, and it's all these soft hoodoos that have formed because bedrock is fairly erodible. And again, this is kind of just to give you a sense of what we're looking at. We're standing on top of the landslide toe here, looking across at all of these hoodoos and the really erodible bedrock valley walls. You can also see the tops of full-grown pine trees that are in the valley bottom. So this shows you the sense of relief from the top of the landslide toe to the base of the channel next to the landslide. So this project presented some interesting questions and interesting complications. We wanted to understand when the West Elk landslide failed and what the relative erosivities were of the landslide sediment and the surrounding topography to see if that could give us any clues as to why the channel diverted around the landslide rather than eroding through it. And it seems like, to answer the question, when did the landslide fail, it would be easiest just to do some geochronology. But unfortunately, we couldn't find any carbon in the field and was not sure that this rock would be suitable for cosmogenic exposure dating. And we also were at the start of a pandemic and unsure what fieldwork would look like. So we kind of turned our efforts to a modeling scheme where we would try and construct a synthetic landscape that represents what this area looked like immediately post landslide. And then we would model that landscape until we got to a landscape that was statistically similar to our current topography. And we would use that age as an estimate for the age of this landslide. So this takes a few steps. We'll go through those. The first was constructing this synthetic landscape immediately post landslide. So essentially, we have a valley wall that has been eroded outwards, and we needed to unerode that valley wall. So we created a straight valley wall segment, which is kind of panels A through D here are sort of the process of doing that. And then we pasted the landslide on top of that topography. And what this gave us in F was a final synthetic landscape that had a large blockage. So we did a cross-section through this red area here and verified that yes, the channel is blocked off. It immediately kind of gets dammed right at this inflection point. And then we did a cross-section across the valley just to make sure that The valley topography that we had created matched what we expected it to look like. So from that synthetic landscape, we then plan to run a Landlab model over that. If you haven't used Landlab yet, I highly recommend it. Essentially, it's kind of a modeling toolbox where instead of having to write everything from scratch, you can draw in these components that simulate different erosion processes. So in this case, we had river incision via stream power, and then we also used hill slope diffusion across the landscape. So we just ran a model with these elements. But before we could do so, we needed to find a couple factors. The main one is this relies a lot on the erosion of the stream, which is set by stream power equation here. Our erosion is equal to a constant K times upstream drainage area to the power M times slope to the power N. And we have no idea what K is for this area. So the first part of Sam's project was trying to constrain what K is, and in particular, what's the erosivity K for the normal stream sections and for the stream that's cutting through landslide debris. So we used a couple methods, and I'll just kind of briefly go over these here. One, we did slope area analysis to try and estimate K, assuming that we know U, N, and M, and assuming steady state. We then also recognize this is not actually a steady state landscape. We're interested in it because it's dynamic. And so then we started kind of running this Landlab model, knowing it's going to be incorrect, but trying to minimize the errors in it. So we would run the model for 20,000 years with different K values and assess how well that our simulations matched our observations using a chi-squared metric and looking for the lowest chi-squared value. We did this for the section in blue to find K for the landscape, and then did it for a section that included the landslide to find K for the landslide debris. Once those were found, we kind of did the same process, but instead of varying K, we varied time and looked for when the simulated landscape best matched our observed landscape. All right, so our results for K showed some fairly similar values. So when we looked at the stream, our chi-squared analysis gave a K value of 8.1 times 10 to the negative 6 and 12 times 10 to the negative 6 for the slope area analysis. So fairly similar. And then in the landslide area, we only did a chi-squared analysis and we got a value of 1 times 10 to the negative 6. So considering all of our error and a lot of the assumptions we made in this model, these are fairly similar values, which indicates that K is similar. And since K depends on lithology, climate, basin hydrology, sediment load, erosion style, as well as other factors, this indicates all of these factors are likely very similar for the area in the landslide and the area upstream and downstream of the landslide. And we look at images, it kind of makes sense. And I don't know why this upper left image has really been unhappy in PowerPoint, but upstream of the landslide, we basically have an alluvial stream system that's probably a thin alluvial cover over bedrock. And then along the slide, we have similarly an alluvial system, although there are these larger boulders from the landslide debris. And that these larger boulders might be why the erosivity in the landslide is slightly lower than elsewhere. So this might be making it slightly harder to erode this area, however, not significantly harder. And then our preliminary ages are also showing that it seems like the best fit for our model was if the landslide formed about 40 to 50,000 years ago, which gives an incision rate through the landslide debris of about 1.4 millimeters per year. This is an order of magnitude greater than the regional incision rates that were calculated downstream along the Gunnison River. But that's not too unexpected and actually is fairly consistent with other landslide dam studies that also show about an order of magnitude increase in incision rates through the landslide dam. What's kind of interesting about this is that this landslide likely caused damming of the channel and a lake to form that extended about 3 kilometers upstream. But there's no evidence of this lake today. And there's also not really a significant change in valley width through the landslide toe. So that seems to suggest that if this landslide is indeed 40 to 50,000 years, that's enough time in this particular area for the stream to cut a new channel and also to widen out to maintain consistent valley widths upstream and downstream of the slide and through the slide. And we're hoping to verify this age this summer with some more geochronology work. So I know I'm running short on time, so just to quickly summarize, we've looked at 3 case studies that deal with sediment and rivers. And in the first one, we looked at how we can change how sediment is moving through a river channel using retention. We found that retention can be significant, and if we lose the sediment retention in a channel, we can cause fairly significant incision and the formation of river terraces. In that same study area in the Tanaway, we looked at how sediment is being delivered via earthflows, and these earthflows are definitely delivering sediment to river channels. In fact, some 25% at least have been recently active, and they're also working to narrow valley widths. Then we looked at an extreme example of valley widths being adjusted in the case where the valley actually moved over because of a landslide, and used modeling and some statistics to estimate a landslide age of 40 to 50,000 years for this landslide to occur and for the valley to erode over. So hopefully I have not bored you as I bored my dog during field work, and I'd love to take any questions.
All right, let's give Sarah a round of applause for an excellent talk. Yeah, that was
great.
Definitely awesome. Yeah. So I guess at this point we'll transition into a Q&A. So if you have a question, if you have to leave at 9, or at least 7 minutes from now, whatever time it is for you, then feel free to put those into the chat. And Mikey and I are going to alternate asking those, posing those to Sarah. So feel free to put those in. I guess to like let me think. Yeah, an initial question. Oh yeah, here we go. So Tyler Doan is asking, thanks, Sarah. Can you elaborate on what MAD is? So the MAD metric.
Yeah, I'll try. So it's a bivariate index. Basically, it looks at, well, so I'm very bad at explaining what MAD is. And Tyler, I will email you the paper. But it looks, you can set the radius that you're looking, and then it's going to look kind of along the flow direction. So north, south, east, west, northeast to southwest, and southeast to northwest. And along each of those 4 directions within the radius that you set, it's looking at what the variation in your topographic residuals are. And I think that's the best I can explain it without having the paper in front of me.
So I have a question of my own here. I was wondering, did you guys do any analysis on what the grain size coming in from the landslides or the earth flows were to those systems?
That would be our next steps. So unfortunately, when this work was being done, field work wasn't really supposed to be going on. We kind of managed to sneak some in by me saying I was visiting family and then accidentally meeting up with my student in the field. But yeah, so initial observations, it's mostly coming out of the Roslyn Formation, which is sand sized and is going to weather away within a year to being sand. And that's mostly what we observed when we dug for radiocarbon, is we're digging through sands that had weathered out from the Roslyn Formation. So it's not actually introducing a lot of coarse debris, it's mostly introducing fine debris. However, now that I know, I think we didn't have a clear sense of which earth flows are coming from the basalt and which from the Roslyn Formation. And now it would be nice to go back and see if there is actually a difference in what those two look like.
Yeah, that would be interesting. It seemed like, and I may have gotten my, where each channel was and exactly what related to what, but in some of the photos where you were were finding terraces with the logs on them, there did appear to be, larger grainy, coarse sediment there. I'm wondering where that came from and if this system is kind of stuck with only fine sediment, and then all of a sudden these logs that can, exert a lot more power come through and you see this high erosion. Yeah, it just seems like an interesting dynamic that would be fun to see.
Yeah, that's actually one reason we started looking at the earth flows is because they're all in the North Fork, and the North Fork has all the alluvium, and the other two forks don't really. And so we thought maybe this was why the North Fork of this system was alluvial. But I think our initial observations is it's something else must be bringing in all of that sediment.
Okay, yeah, definitely. I should go to the chat and see if somebody else actually has a question.
Just words of praise so far. So thank you for a great talk, Sarah, from Tim Abbey. And yeah, the recording will be available too for this talk on the EPSP Connects website. We'll be sure to share that. I guess one question I had too, in terms of those really, especially the West Elk type landslides too, the really channel spanning ones, in terms of like modeling and everything. Is the model taking into account, like I'm imagining that the landslide material is kind of cannibalizing itself versus then the upstream sediment supply? Do you have any thoughts like in terms of like being able to parameterize that or like the relative impact of each of those processes?
We did some grain size analysis. So we were also kind of curious. And we looked at the grain sizes in the active channels, and they're not that different from the area in the channel and upstream and downstream. It may be that during that initial erosion around the toe of the landslide, then you might see more of that cannibalizing factor. But I think also part of this is just the nature of this breccia is really erodible. It's really easy for the breccia to fall apart into more of the cobble to gravel sized andesite clasts that make up the breccia.
Looks like we have a question from Vanessa. She wants to know, in the West Elk case, you referred to sidewalls being very erodible, but the landslide material representing a slightly more erosion resistant area. So kind of what you guys were just talking about. Can you say a bit more on why the erodibility changes between the material when the material is intact with the sidewall versus deposited in the channel?
That's a great question, Vanessa. And something that I didn't realize when I started working in this area is I don't think that geologic maps are accurate. And so part of this is I have no idea what is actually making up the head walls on either side, because there's this interlayering of some pyroclastic flows and breccias and some andesite flows. There could be some differences in where exactly it's being sourced from. However, a big puzzle for me currently right now is the paleo flow directions that are in the breccia and the pyroclastic flows do not match with where geologic maps say this is supposed to be coming from. So if anybody is good at investigating this, I would love somebody to help me make an accurate geologic map of this area and do some volcaniclastic studies and paleo current directions. Yeah, Vanessa, I'm not quite sure exactly where erodibility changes. It may be slightly different flows that it's being sourced from the west wall versus the east valley wall. And yeah, I think there's a lot of further investigation to do there.
So thanks. And so the next question we had from Davey in the chat was, based on the earthflow mapping, most of these sediment inputs are in the middle and north forks, but the LiDAR indicates many much smaller landslides along the southern margins of the middle fork and west fork. Are these materials just more rapidly evacuated from the system due to lack of in-stream roughness, or are the mechanisms of those slides just different or something else?
Yeah, I think there were 15 landslides early along the middle fork and west fork, if I'm remembering the number correctly. They do tend to be smaller. The relief in that area is also lower, so the total amount of material in those landslides may be a bit less. I think, so just from the last few times I've been back here, there actually may be a switch where these rivers have been bedrock for a while. And I think now we're beginning to build back some of those roughness elements. And so I think some of that newer landslide material in the Middle Fork and West Fork will actually stay in the channels now. But that's, I think, something to be tracked over the next couple decades. So I think historically, these were just more easily evacuated from the Middle Fork and the West Fork compared to the North Fork. But I think that's also about to change.
See if we have more questions here. James, did you refer to the one from Rebecca already?
No, that one's up next. Yeah.
Okay, that's what I thought. So yeah, we have a question from Rebecca Harries. I hope I pronounced that right. She wants to know, with respect to the last section, did you also look at changes in the river profile concavity? So the M/N in response to the landslide. This is something I thought about as well. I'm super interested to hear this.
So we didn't look at anything in the model. We did look at overall concavity of it currently. But so when Sam started this work, all we had was a 10-meter DM that had a bunch of errors in it. I don't know if you noticed in our images of the DM, there's all these crosshatched lines. As soon as Sam submitted his thesis, the USGS 3DEP program released the 3-meter LiDAR for this area. So we haven't gone back and looked at it with this more high resolution LiDAR. And I think that actually would, if we wanted to try and extract concavity currently, I would rather use that data set than the 10-meter that had all those errors in it.
Mm-hmm.
And we didn't really look at it through time, but that would be an interesting thing to look at next.
Yeah, that would be really fun to see. I wonder what that would look like. I'm sure it would change with the landslides coming in, but
yeah.
Well, we'll give it maybe another second for questions to come in. While we're doing that, though, we'll maybe announce next month's EPSP talk. We have Kim Uper. She's going to come and talk. Her title, the talk title will be Islands in the Rain, and this talk will be isolating the influence of rainfall on erosion on volcanic islands. So it should be a really fun talk. It's going to be on Wednesday, February 17th, kind of at the standard time, same as this one. So we're really excited to host Kim and hear from her. And yeah, if anyone has any last minute questions,
you can also feel free to unmute too if you had any other questions, folks. Or...
Yeah. Seems like we're having a bunch of people just excited about your work and saying thanks for the talk. So yeah, we might call it there then. Risa and James, do you guys have anything else?
Nope, that's it. Let's thank her one more time for an awesome talk.
Yeah, that was great. Thank you, Sarah, so much.
Yeah.
Oh, thank you for the invitation.
Okay. Okay, so we'll be seeing you, I guess. Did you have a paper coming out? I thought you said.
We have revisions for Peyton's work right now.